Now here some this something are the bands, radio bands. So we should understand what are these radio bands and what is this frequency allocation. So these are the basic concept. That is extremely low frequency, 330 to 300 hertz. This is appropriate wavelength, that is 10 to 1 micrometer, and ultra low frequency 300 to 3000 hertz, very low frequency 3 to 30 kilohertz, low frequency 330 to 300 kilohertz, medium frequency 300 to 3000 kilohertz, high frequency 3 to 30 megahertz, very high frequency 30 to 300 megahertz, and ultra high frequency 300 to 3000 megahertz, super high frequency 3 to 30 gigahertz, and extremely high frequency 30 to 300 gigahertz. So 30 to 300 gigahertz, we don't have anything in this. 3 to 30 gigahertz, we have something, that is whatever the vector network analyzer we have, it is up to the 14 gigahertz. Okay, few kilohertz, I think the 300 kilohertz to 14 gigahertz. So we can measure this frequency. We have that at the institute. It is very costly instrument, but we have it fortunately. Ultra high frequency, this frequency we do use very high frequency. This also we have the application FM radio, this that high frequency. From here generally the antenna start working, and this kilohertz, previously the old applications are there in this frequency, some are in this, and these lower frequencies generally in communication are not used, these higher frequencies are. So this is a general bifurcation of the frequencies in terms of the comparative measure, high frequency, low frequency, very low, this way. So previously it was used. Now there are some other these are the IEEE band. Now this IEEE band are there. This generally this is a further bifurcation, and radar band, although this is the radar band called, but these frequencies can say the microwave frequency. So L band 1 to 2 gigahertz, 2 to 4 gigahertz S band. Whatever the applications are there or papers, if you will search research paper, some titles include the band, which band the operation is there. Then 4 to 8 gigahertz C band, 8 to 12 gigahertz X band. We have a microwave bench in our institute for this particular band, X band, 8 to 12 gigahertz. That is for micro engineering, not in your subject. 12 to 18 gigahertz KU band, then 18 to 27 gigahertz K band, 27 to 40 gigahertz Ka band, 40 generally these bands are used, 40 to 75 V band, and 75 to 110 W band, and beyond 110 till 300 it is called millimeter wave. So millimeter band. So this is what the band, whatever the applications we have, that I have mentioned here to you, and this micromillimeter band is there further. Now why antenna radiate? Just now we have covered that why antenna radiate. So it need a acceleration and deceleration. That is the very essential part is your time varying signal. If you will have a time varying signal, then and then you can have the radiation of the antenna. If you will have a DC signal, then antenna do not radiate. Okay, antenna radiations will not be there. So very essential part is the time varying signal is required, acceleration and deceleration is required. In further, whatever the wires we are using, generally we are saying the wires are the radiator. So this way, this is what the source, transmitter line, antenna, and in free wave, the antenna will get radiated. These are the bend curve. These are the requirement. If there is there, then it will get radiated. And wire bend. So I have taken the example of the wire bend, and here you can have the radiation. This way, the whatever the radiation is there, if the bend is there, at the bend the radiation is more. Okay, so this is what the electric field intensity accordingly it has been shown. This way we can understand the animation help us to understand the radiation. Accordingly we can understand and go further. Now we will go for understand the type of antenna. There are so many bases that on what basis we can divide the antenna. So there are some parameter. So basis on frequency of operation. If you are using for low frequency of operation, high frequency of operation, or as just now I have mentioned the bands, various IEEE bands. So this various IEEE bands also give you the bifurcation of the antenna. So basis on frequency of operation, you can bifurcate. Then based on the physical shape, some are the planar antenna, some are the wire antenna, some are the you can say aperture antenna, means dish antenna, and horn antenna. So these are the aperture antenna, wire antenna, dipole antenna, loop antenna. These are the wire antenna. Planar antenna, that is microstrip antenna. These are the planar antenna. Directivity. So based on the directivity, how the radiation pattern is there, it is radiating in all the direction or whether it is focused in particular direction. So based on that, we can have the bifurcation. So these are the base that on what basis we can bifurcate the antenna. So these antenna can be bifurcated on the this is monopole, dipole, loop antenna, that is electrically small antenna, that is VHF frequency. Then resonant antenna, that is VHF, again lambda by 2 dipole antenna, lambda by 4 monopole antenna, microstrip pack antenna. Aperture antennas, that is mainly are the UHF, that is ultra high frequency, that is the reflector and horn. Just now I have told. Broadband antenna that covers the log periodic helical and the spiral antenna. So these are the types of antenna. Then the wire antennas, then aperture antenna, microstrip antenna. These are again the type. Then array antenna, then reflector antenna, then lens antenna. So these are again the type of the various antenna. Based on this can be bifurcated. So this is the basic thing. So this is what the antenna picture. This is the dipole antenna, wire antenna, loop antenna, helical antenna. These all comes under the what? Wire antenna. These are the aperture antenna. This is what planar antenna, patch, microstrip antenna. And this is what the other Yagi-Uda antenna. So this is what you can say the array antenna. Multiple arrays are put this way. These are reflectors antenna. This reflection example is your dish antenna. So these are the some of the pictures I have put so that you can understand what are the types of antenna. Based on the radiation pattern, we can bifurcate the antenna into 3 types. So what is very first? So very first is the isotropic radiator. So this isotropic radiator, this is isotropic radiator. It is the hypothetical term, and lossless antenna having equal radiation in all directions. So the antenna which is radiating in all the direction, like a sphere. If you will have a ball sphere, and inside it at the center you will have an antenna and it is radiating all the direction. Practically this type of antenna is not possible. but this is taken as a reference, ideal case. And with reference to the isotropic antenna radiator, we define the other antenna. So this is a reference antenna. Omnidirectional antenna. The radiation pattern is non-directional in azimuth plane and directional in the elevation plane. Now, very first, you just understand what is azimuth plane and what is elevation plane. Can anybody tell me azimuth plane and elevation plane? I'll put this notepad or this is this. Okay, so this is what plane? Azimuth or elevation? XY plane. This is azimuth. And if I'll put this way, this is elevation. Elevation is simply elevator means going vertically upward and down. So this is elevation plane. This azimuth, horizontal. So horizontal and vertical. Okay. So what it is saying that the omnidirectional, the radiation pattern is non-directional in azimuth. This azimuth. It is non-directional, means in this plane, XY plane, it is radiating in all the direction. Here, all the way. Okay. Radiations are same. But in elevation, it is directional. Elevation, it is not, mostly it is very low radiation. Elevation, this one, it is direction. So it is, you can say here, same. Directional antennas, so they are specific. They are radiating in a particular direction. Okay, radiating, the focus is in this direction only. So based on the angle, we can consider the directional antenna. Okay, so having a property of radiating or receiving electromagnetic wave more efficiently in some direction than in other. So the intensity is more in this particular direction, and as compared to this direction, other direction, there is very low intensity. So this is called, these are the three basic type, and we'll require these three basic type further. Okay, because these are very basic, and with reference to mathematical calculation and all these three basics are required. Now, this is omnidirectional antenna, and this is directional antenna. Now, this is called omnidirectional antenna. Omnidirectional means, as I shows this XY plane. Okay, this is 3D pattern. In XY plane, all it is sphere, but in the vertical plane, it is not similar. It is this way. Okay, so if I will take reflections here on this wall, so it becomes a 8. This reflection I take on this wall, it becomes this. If this reflection I take on the down wall, so it shows me the square. Okay, so the omnidirectional antenna, it shows 8. So in your book of Balani, it's showing this, the figure of 8 this way. So this is called 2D pattern, and this is 3D radiation pattern. This is also directive antenna. This is also the radiation pattern. So it is particularly directive antenna. It is radiating in this direction, front side, and these are called the side lobe. We will discuss afterward. So this in this direction, the radiation is poor. It is more focused in the front. Okay, so this is directive antenna. Now these are the parameters. Now we have to go for the antenna radiation parameter. Antenna radiate. So for understanding and measurement, we must know the radiation parameter, which is your first unit. So here radiation parameter. What are the radiation parameters? So before going to radiation parameter, I'll give you the this I covered in these previous electromagnetic. So I'll just give you the description in the group, and you just go through the spherical coordinate system. I'll give you the link of the videos, and you just refer it because we don't have the time. You can refer it and go further. So these radiation patterns are required, or sorry, not radiation pattern, coordinate systems are required to understand, so that we can go further. So these coordinate systems you can just understand. So this is what the spherical coordinate system, mostly we are using spherical coordinate system. This is our increasing radius, and this is what the angle phi. So this angle is azimuth angle, that is the horizontal angle. This door is rotating, and at this, if I'll say this is the x-axis, so at x-axis it is 0, and accordingly at here it is 90, then accordingly it will rotate. So that way we can find it out the angle. You just go through the video for the more detail. Then this is the theta. This is the elevation, that is the vertical angle. And the whatever the maximum degree of this is 180, and for previous it is alpha, it is 360. Why it is? You just find it out. Then we will antenna radiation pattern. So what is the radiation pattern? It is the mathematical function or a graphical representation of a radiation pattern of antenna as a function of space coordinates. So we are understanding the radiation, how antenna radiate. So we are graphically representing it and representing mathematically. Mathematical function or a graphical function, both way it is represented. As I have mentioned here initially, the isotropic pattern. It is what the definitions I have mentioned here: the isotropic pattern, then the directional pattern, and omnidirectional. So these three are repeatedly we require. So isotropic is a hypothetical term, equally in all the direction, directive in a particular direction. Whatever the antenna we are studying, that mostly they are the directive antenna. Some are the omnidirectional antenna. The basic antenna, that is dipole antenna and all this, they are omnidirectional antennas. Now, antenna radiation pattern. So this is what a directive pattern I have put, so that we can understand how we can bifurcate the antenna and how bifurcation is there in the antenna. So this is what radiation lobe. Okay. So what is this radiation lobe? A radiation pattern boundaries by the region of relatively weak radiation intensity. So this is what we have taken a particular intensity. So beyond this is a very weak intensity, and inside this is having the high intensity. So whatever these boundaries I make here, okay, this way. So this is what called the radiation pattern. Now here there are multiple lobes. So this, in this radiation pattern, whatever this lobe is the major lobe. Okay. So this lobe, whatever this lobe is the major lobe. So this lobe, blue, this is called the major lobe. Minor lobe, this all small, apart from the major lobe, all other lobes are called the minor lobe. All are the minor lobes. But in the minor lobe, again, there is the bifurcation, that is the side lobe and the back lobe. So this is side lobe, those they are adjacent to the main lobe. So this is side lobe, and those they are at the back side, they are called the back lobe. So this is what the one general pattern. And what is this parameter, that also we'll discuss. Then front to back ratio. Front to back ratio in antenna design you will require. That is how much is the front lobe and how much is the back lobe. So ratio of that. Based on that, how much the antenna is directive is decided. It is this side lobe and back lobe that are the unwanted in most of the application where we are using the directive antenna. So this front to back ratio, it should be higher for particular. Now, whatever this pattern I have shown previously, this is in one way. So this is the other way representation of the radiation pattern. So this is what the linear plot. Here, this is what the main lobe, and a degree is 0 to pi, again 0 to pi. This way also represent. So this is the main lobe, these are the side lobe, and these are the back lobe. So this way it is also represent. This is half power beam width, and this is first null beam width. What it is? Now this is your maximum power. So this is half power. How you can take half power? Whatever your maximum multiplied by 0.707, or if it is in dB, then 3 dB down. Here, if it is 10 dB, then 3 dB down. So is whatever the point you get, you just join this, and whatever this angle, yeah, whatever this is called the half power beam width. We'll go in detail further. First null beam width, this is the major lobe. Here you get the null, here you get the null. So this is what first null beam width. This is the beam width. First null beam width. This way also we can measure. So these are the some parameter related to the radiation pattern, that is the major lobe, side lobe, back lobe, and the minor lobe. Now antenna radiation pattern. For the antenna radiation pattern, what you will require for a complete specification of radiation pattern. So here now the derivation and the mathematical parts will go. Now, as I mentioned, the theta and phi, these are the most important parameter because we are going in this parameter. Theta is angle with z-axis, vertical, and phi is this angle, door. Whatever the animation I have shown for the door, this angle is what? Phi, and vertical angle, this is theta. Electric field representation, that is the function of E theta, and it is function of both theta and phi. The electric component along the phi component, E phi, again it is representation of both. Normal field pattern for the component, that is electric field representation E theta, generally it is taken E theta is function of theta and phi, both in the normal direction. So it is E theta in particular direction to the E theta of the maximum. This way that ratio can be calculated. Antenna radiation pattern is calculated here. Maximum electric field intensity in the particular direction. So if I'll take this example, so here maximum electric field intensity in this particular direction. Here this is the reference E theta phi. This value is taken, and where you will measure, you can take this point, any point. Accordingly, you can measure. So maximum, this is what you can do the normalization of radiation pattern. So maximum point will be 1, and less than 1, the other point will be there. So it can be done in general or in terms of dB also. Okay, in dB also that can be done. So this way is the representation, mathematical representation. Now this is what the simulation softwares, they use such type of radiation pattern, and you can see. So the red is the highest radiation intensity, that mostly the electric field intensity, and blue is the red. So here this is the directive antenna, the red one is here, so it is in this direction, and the blue one is here. So here I have just given the example so that you can understand. So this is in this particular direction. Then the next parameter is the radiation power density. So the radiation power density, along what direction, what radiation is there, and how the radiation power density can be measured. So this radiation power density, how it can be measured. So here the Poynting vector formula, Poynting vector theorem is required. So Poynting vector is quietly considered here. Its name is, this is regarding the Poynting vector. The name of the scientist was Poynting. So this is given a name of Poynting vector. So the radiation power density is what? This is the simple detail about that. It is the vector product of electric and magnetic field, is what the Poynting theorem says there. And Poynting vector has the dimension of power per area. So this is related to the Poynting vector. Poynting vector theorem is there. So accordingly, we can consider the Poynting vector concept. Now, what Poynting vectors they say there? So whatever the power radiated, the PAV, that is the average power. So this is the average power radiated by an antenna, any antenna. So whatever the average power radiated is the whatever the radiation and D dot ds. Sorry, W radiated radiation, whatever the radiation, and the into ds. Ds is the surface area, and this is what surface integral we are taking. So simply it is the real part of E cross H. This is Poynting theorem. E cross H. What is Poynting theorem says? Poynting theorem says that if the electric field, magnetic field, and direction of propagation are perpendicular to each other. This is electric field, this is magnetic field, perpendicular to each other, and this is direction of propagation. Okay, they are perpendicular to each other. This way is the simple statement of Poynting. The total power radiated by the isotropic radiator, that is the total power radiated, can be given, again same concept is used. Now we are putting the integral form. Now whatever the concept of your coordinate system is, we are applying here. Now what we had discussed previously, if you remember, if not, then refer the video for the coordinate system. We have taken the surface integral of 0 to pi and 0 to 2 pi. Why 0 to pi? Because theta limit is, maximum limit is 0 to pi. Why 0 to 2 pi? Because alpha maximum limit is 0 to 2 pi. And what is this? The W0R. This is what the power radiated, and what entire surface AR is along the radius r square sine theta d phi. From where it is comes, as it is the sphere, it comes from the coordinate system, spherical coordinate system. So for that you have to refer that video. So if you will take this, then the result of this, if you will solve this, that is 4 pi r square W0. So 4 pi r square W0 is power radiated, and power density is power radiated, whatever the power you are radiating, divided by 4 pi r square. Why 4 pi r square? Is the sphere, because we are assuming that the power is radiated in all the directions. This is 4 pi r square is the area of a sphere. So P radiated upon 4 pi r square. So this is the formula for the radiated power. Okay. Now radiation intensity we are going for. So radiation intensity, it is defined as the power radiated from an antenna per unit solid angle. So whatever the power radiated, antenna per unit solid angle. Previously, now radiation density we have taken it for the entire lobe, and that we are considering. Now we are considering for a per unit solid angle specific. Solid angle is three-dimensional, as I have taken in a coordinate system. I have given the example of watermelon, a cone. So that is what the solid angle. So that solid angle is considered here. So this is a radiation intensity. So repeating again and again, that coordinate system concept should be clear. So you get it clear. So this, whatever this diagram, it should be clear to you. It is given in the coordinate system concept. So this is what, whatever this angle is given, it is what the solid angle. Now for linear angle, that is simple 2D angle, the 360 degree is given, and for a solid angle, that is 4 pi r square upon r square. So 4 pi is the solid angle. 2 pi r is what your normal angle, planar angle, and 4 pi is your complete solid angle. Here, U is the radiation intensity. Now, two parameters are there. Previously, we discussed radiation density. That formula given. Now we are talking radiation intensity. It is also this is different. U is the radiation intensity. We require this multiple time further radiation intensity U for all the parameters. So remember it. So U is the radiation intensity. The unit is watt per unit per solid angle. Okay, watt per unit solid angle. U is the radiation intensity. It is represented as U, theta, and phi. As I mentioned that we are using the spherical coordinate system, so theta and phi will be there. Okay, so u theta and phi, this u theta and phi is what, how you can represent radiation intensity. It is represented simply a power along direction of theta and phi in a solid angle of d omega. That is what the watermelon example I have given. In a particular angle, whatever the power along this particular direction in the solid angle of this much upon the solid angle. That is, you can say, take a major lobe, and what is the solid angle of that major lobe? So you just take power along that direction. What is the power along that direction you are taken upon solid angle? So power along that direction is given here, and into r square upon dA. Okay, that is what the aperture. Okay, so here power density into r square. Power intensity and power density, I have given the relation. This is power intensity equals to power density into r square. Okay, power density is power along that particular direction upon the aperture is power density, and if you will multiply by r square, so it will be power intensity. So this is the relation between power density and power intensity. So the total power is obtained by integrating the radiation intensity. So P radiated is given by this. You just take as sphere we are taking, because the radiation we are considering in all the direction. This is P radiated is equals to 0, this pi 0 to 2 pi, theta 0 to pi. Always we remember this for the complete sphere. Theta is 0 to pi and phi is 0 to 2 pi. U is the radiation intensity, sine theta d theta d phi. Okay, so d omega is the element of the solid angle, is represented by this. Okay, as the description is there. For a isotropic source, if your isotropic source is there, that is along, isotropic is along the horizontal, that is azimuth, same radiation is there, and elevation there may be the directive pattern. So for an isotropic source, you will be independent of the angle theta and phi. So power radiated is the 4 pi for the entire what you can say sphere, u0 into d omega. So u0 is constant and d omega is 4 pi. So 4 pi u0. So for isotropic radiator, power radiated is equals to 4 pi into u0. U0 is what? Your radiation intensity. Okay. Power radiated is equals to 4 pi into radiation intensity. So u0 for isotropic radiator, radiation intensity is power radiated upon 4 pi. So these formulas you will require in the simple numerical to solve and to understand. So this way it is the radiation intensity. This radiation intensity, these are the examples. This is the solid angle example. This way you can understand the solid. This is radiating and this particular angle is considered. So this is, you can consider the solid angle. These are the simple example. So these are the things in next topic, next lecture, we will cover the directivity. And why directivity is there? Again, it is in terms of the radiation intensity, radiation density. So the two should get clear. And based on that, instant intensity and density, we will go for the directivity. So